once around the Andromeda Galaxy. The Andromeda Galaxy, one of my favorite objects in the sky, lies in the constellation of Andromeda, which is really laid out as a couple of lines that converge on the star Alpheratz, which is also a corner star of the Great Square of Pegasus. So it's kind of shared between the two constellations, and that is Alpha Andromeda. The most obvious other stars are the Delta star, Beta star, which is called Mirac, and Almach at the end there, which is Gamma, the third brightest. And it's easy to find those from the Great Square because of that shared corner star. So if you start from that corner star and head along that line to Delta, and then following the green line up to Beta, Mirac, and turn right and go past a couple of fainter stars, Mu and Nu, then you find the Andromeda Galaxy as a fuzzy patch in the sky that you can see with the naked eye. Charles Messier put it in his catalogue of annoying things that were not comets. In his list, it was number 31, and this is a list of things that people used to keep reporting to him as a great comet hunter. He would get these reports when people thought they'd found a comet, and he had this checklist of things that had been seen before. So number 31 in the Messier catalogue. As I say, you can see it with the naked eye, but what you're really looking at is the bright nucleus of it. The full extent is about 5 times the area of the full moon, and we've got the full moon there shown just for scale comparison. I very much doubt you'd actually see these two in the sky like this. Best viewed with low magnification with binoculars, or with the lowest possible magnification you can squeeze out of your telescope, because it is such a large object on the sky. Now, we now know that it's 2.5 million light years away, and the distance between the Milky Way galaxy and Andromeda is about 20 times the size of those galaxies. So Andromeda is slightly larger at 220,000 light years, and you'd fit 10 and a bit of those in the gap between, or 20 of the Milky Way in the gap between, depending on which way you were going. We know the distance because it was one of the things that made Edwin Hubble famous. He located a variable star called a Cepheid variable in the Andromeda Nebula, as it was then known. And that's marked at the top of the diagram, which is in the negative. So bright things are shown as black in this picture. So we have the nucleus of the galaxy in the middle, some of the dust lanes around it, and then bright stars marked as little dots. And up the top there, between the two black bars where it says var, that's the variable that he found. The N has been crossed out, and a couple of other N's there in this photograph of the 6th of October, 1923. N stood for nova, which marked a star that had appeared as a transient, wasn't there in previous photographs, and then went away again. But he's crossed out the N for this one and written var because it's a variable star. And these bright variable stars, called Cepheid variables, have a very useful property, which is that they pulsate, and the period of their pulsation relates to how powerful they are, how much mass there is, and how much light they give out. And so if you know the power of the star, and you can compare that with how bright it appears from Earth, you can infer the distance. And we can't know the power except for the fact that there is this relationship, which means that if we just watch the star pulsating, the time between the pulsations can just be read off to give us the power output. And then from there, we can work out the distance. And this was first discovered by Henrietta Leavitt Swan. She identified a whole bunch of these Cepheid variables in the Large Magellanic Cloud. Now, the Large Magellanic Cloud is a dwarf galaxy that orbits around the Milky Way and is about 160,000 light years away, and only a few light years across. So any star within it was to within 1% at the same distance from the Earth. So all these Cephids are at the same distance, and therefore their apparent brightness is directly correlated with their true power output. And if you compare that against the period, you get this nice straight line, which tells us that these are nature's standard candles, and we can use them to infer distance. And that's exactly what Hubble did, and he got a figure of about 1 million light years. Now, that's not quite right. The modern figure is more like 2.5 million light years. And the reason for that was figured out in the 1940s while Walter Bader worked out that there were actually two classes of Cepheid variables, both with the same type of relationship, shown in this graph here as the yellow and the blue stars. And they are roughly equal in slope, but slightly shifted on the diagram. And so if you don't take account of the fact that you have to work out whether this is a younger population one, more massive Cepheid, or an older, fainter population two Cepheid, then it can be confusing. And having done that and then reassessed the distance using Hubble's variable in M31, we get a value of just over 2 million light years. So twice the distance that he estimated, because he didn't know that there were two classes of Cephids to be accounted for. So Andromeda is just over 2.5 million light years away from the Milky Way, and these are the two largest galaxies in what we call the local group. The third largest is Triangulum. It's about 10% the size of the Milky Way. And then we have the large and small Magellanic Clouds, which are dwarf galaxies in orbit around the Milky Way alone, along with a bunch of others. And then Andromeda has a group of small dwarf galaxies orbiting it as well. And one or two wanderers that seem to be in between, like NGC 6822 there, that's kind of halfway between the two. It's a slightly larger galaxy, a little bit bigger, 220,000 light years across and 1 trillion stars, compared to the 400 billion that we think are in the Milky Way, although that's not an exact figure because we can't see all of it very well. Lovely photograph here, and it shows the bright nucleus and the material swirling around it, the dust lanes, and it shows a couple of the dwarf galaxies as well, which we'll come on to. You can also begin to see a couple of interesting things here. One is that the disk of the galaxy looks a bit warped, and the other is that there aren't really any properly defined spiral arms. These are more rings around the galaxy than they are spirals. Another photograph here, taken by my good friend Paul Beskine, an amateur astronomer of this area, but his photographs are truly amazing. And this one is constructed using 3 different filters. Red is hydrogen gas, green is oxygen, and the blue is the emissions from sulfur. By using this particular palette of colors, you pick out the structure within Andromeda very well. And again, you can see the slight warping of the disk. Seems to be raised on the left and lowered on the right. And you can see the structure within the dust lanes and the red star-forming regions. And the true full resolution of photograph that Paul has done on this one is astonishing. You can zoom right in and see all those star-forming regions in and around the arms of the Andromeda Galaxy as clear as if they were in the Milky Way itself. Now, there's a very curious thing. We've got these star-forming regions with bright young blue stars in the center, pouring out ultraviolet, and that's ionizing the hydrogen gas and making it glow red. But overall, this is actually the case that the Andromeda Galaxy seems to have been forming fewer stars recently than the Milky Way by about a factor of 6. So things have slowed right down for it, and we're not quite sure why that is. When we look at its companions, we see 2 of these dwarf elliptical galaxies in orbit round the main galaxy. M32 is just a little bit further away, 110,000 light years beyond the main structure, and was the first elliptical galaxy to be observed. Typical of elliptical galaxies, it's got lots of old small stars, red ones and yellow ones in it, and practically no gas and dust. And not much star formation has been going on recently, and hence any giant stars that would have been very massive have already burnt out. They wouldn't last very long at all. But there have been some detections of hints of a pulse of recent star formation. So that's probably a few 100 million years ago now. The other companion, M110, well, that wasn't really a Messier object in the original form of Charles Messier's catalogue. It was added later, but nevertheless, we call it M110. There's also an NGC catalogue number for it, NGC 205. But this is likely to have been a dwarf spiral galaxy, smaller than Andromeda, smaller than the Milky Way, that has come too close to its large neighbour and had all its outer layers removed, leaving just the central bulge and nucleus of the galaxy to appear to be this elliptical blob. And we think that it was a significant spiral galaxy with its own family of around 30 dwarf galaxies orbiting around it when it encountered the main Andromeda Galaxy. And that stole not only all the gas and dust, but it also stole those 30 dwarf galaxies and made them its own. So those are now added to the collection that are all in orbit round Andromeda. Very similar story with globular clusters. The Andromeda Galaxy has over 400 globular clusters, each with their G number marked on this little photograph here. And that's many more than the Milky Way, which has something like 150, I think. And again, some of these may have been delivered accompanying the merger or the near merger with M110. Also in the center of this photograph, you can see a very bright cluster of hot blue stars, fairly young stars, glowing away very brightly, NGC 206 there. And it's at the junction of the two different dust lanes, which is very interesting indeed. Here's another globular cluster picture. This is G1, the first one to be discovered. And this contains an intermediate mass black hole of about 1,000 solar masses. And again, we think this is most likely the central nucleus of a dwarf galaxy that has lost its outer layers to its rather cannibalistic neighbor. The giant Andromeda Galaxy has stripped all these down to their cores. Their cores are such that all of these stars are gravitationally bound. They're all within the overall Hill sphere of the total mass of the nucleus. So they stay together, but the more weakly bound outer layers get removed by the presence of the giant structure right next door. And when we look at Andromeda, we do see a number of curious features. I've already mentioned the circularity of the dust lanes. They're not really spirals. It's not really showing spiral arms at all, this galaxy. It's also got a warped disk. It's got that large star cluster, NGC 206, far larger than any similar cluster in the Milky Way. And then there are some very strange things going on in the nucleus. But first, let's have a look at the two dwarf galaxies that you can see, one above and one below the main galaxy there. So Messier 32, we think a few 100 million years ago, it ploughed straight through Andromeda and out the other side. And in the process, lost all of its outer gas and loosely bound stars, just leaving that central elliptical blob of a nucleus behind. And in the process, it probably created the circularization of the ring patterns around the main galaxy. So this is quite common. Ring galaxies quite often form when one galaxy punches through another and creates this circularization, almost a circular set of ripples. So we think that's what M32 has contributed to this. M33, the Triangulum galaxy, lovely photograph here, with all those marvelous star-forming regions within it and slightly fluffy appearance, has also, probably longer ago, had a near miss with the Andromeda Galaxy, and that may well have been what's warped the shape of the main galaxy's disk. Here again is the NGC 206, the bright star cluster, absolutely monstrous number of stars within it. Nothing like that in the Milky Way. You can see it in the main photo at the join of those dust lanes, and then inset slightly larger. If we zoom in even further, you get a bit more detail of it here. And again, this is possibly a tidal interaction of the gravity of either M32 or M33 with the main galaxy that has triggered off a massive burst of star formation just in this one spot. But there is another intriguing possibility with Andromeda, that way back in the past, it was actually formed from two large spirals merging together. And maybe this is partly responsible for some of those features. But this would have been many billions of years ago, can't account really for the young star cluster NGC 206, but maybe for the circularization and the warped disks. So maybe these two galaxies combined to form this one monster. Now we know that our Milky Way has undergone a similar process. We've even got a name that we've given to the merging galaxy, Gaia Enceladus. And we see that Gaia Enceladus brought its own population of stars, which are chemically slightly different mixtures and different ages, to form the Milky Way. So the process of galactic archaeology is gradually uncovering the history of all of these ancient mergers. But if we drill down into the nucleus of Andromeda, we can see with this X-ray picture from NuStar, a lot of X-ray emitters, X-ray binaries, where a pair of giant stars have evolved. One of them has gone through the phases and collapsed down to a black hole or a neutron star, while the other has then later expanded into a giant and loses its outer layers, stripped away by the gravity of its neighbor, and that then spirals down and gets very, very hot and emits a lot of high energy radiation, ultraviolet and X-rays. And you can see in the inset at the top there the bright blue dot that seems to be coming from the very center of M31. And when we look into that center with Hubble, we find that there is something curious, a double nucleus. You can see it in the inset picture there. You have a bright region, which is clearly a binary structure. There are two areas to it. And when we look in extreme detail with Hubble in an image spanning just 40 light years, you can see the classical nucleus, the bright bit. That's the position where we see the nucleus when we look at it with our telescopes. But just off to the right, there is a bright dot, brighter than the surroundings, fainter than its main classical nucleus. And that is where the center of mass is. It's the true center of Andromeda. When we look in more detail again, we can see in color here that there are three structures, P1, P2, and P3. And P1 and P2 are red in color, indicating gas and dust and stars mixed together. But P3 is very small and very bright and blue. And in fact, there's a lot of ultraviolet and X-rays coming from there. This is M31 star, the supermassive black hole of many millions of solar masses, right in the center, the controlling gravitational mass in this region, surrounded by a cluster of A-class hot young stars and a lot of gas and dust but this is the supermassive black hole being placed in that situation. Now, when we look again at the overall galaxy, another of Mr. Beskin's photographs, but this one is a combination of hydrogen alpha single narrowband and a red filter continuum background of a wider spectral characteristic. And what he's done is subtracted one from the other so that the hydrogen alpha line has been picked out in extreme detail here. It's a very, very powerful technique, and it's showing those ring structures as bright, and it's also showing something rather interesting that wasn't discovered until the 1980s, and that is the nuclear spiral right in the center of Andromeda. And I've got an even better photograph of it. Again, Paul Beskin, and thanks, Paul, for letting me use these images. I was absolutely stunned when I first saw this. It's in the negative, so the bright bits are dark in this image, but you can see that there appears to be material swirling and spiraling in towards the center, perhaps the gravity of that M31 star supermassive black hole at work here. And what we're not sure about is this a flat spiral, a tilted spiral, or is it a spherical structure of material all chaotically trying to get into the center as it's spiraling to its doom? So more study required on that one. Going to the outer part of the galaxy, it's massive. The halo extends 2 million light years out from the center of the Andromeda Galaxy, which is almost all the way over to the Milky Way, in fact. And so there's a huge envelope of mostly hydrogen gas. And again, this all points back to these historic mergers having blown huge amounts of material out beyond the galaxy. So quite incredible what we're beginning to learn about Andromeda. And we, of course, know that it's coming our way. The Milky Way and Andromeda are approaching each other at well over 100 kilometers per second. I have seen figures as high as 163 kilometers per second. I suspect that's 100 miles per second, really, though. And this is detectable through the Doppler effect, the blue shift of the light. So in about 4.5 billion years, the Andromeda and Milky Way will merge. Presumably it'll be called Milkdromeda, if there's anyone still around to do that, because that's about the same time that the sun runs out of fuel. So it's a bad day for planet Earth. Talking of planets, though, we've discovered probably the first exoplanet in another galaxy, an extragalactic planet. Not by direct observation. Indeed, this was detected by microlensing. So a small star, perhaps with a planet around it, passed in front of a distant star, and the result of that was it created, through the mass bending space-time, according to Einstein's general theory of relativity, it curved the space-time around itself, and as it passed across the line of sight, the image of the more distant star was affected by that and made suddenly brighter, as if a lens was focusing the images towards us. And so the light curve raised to a maximum and then faded away. But there is a small blip, and that small blip suggests a planet about 6 times the mass of Jupiter was in orbit around the intervening star. Now, the problem with this technique, really frustratingly, is these events only happen once. So what you can't do is hope to observe it again, making another flyby, another transit event, and see if we can confirm the data. So a very difficult thing to follow up on. But if this is confirmed somehow, then that would be the first detection of a planet in another galactic system 2.5 million light years away. Since this one, we've actually found some in other galaxies even further away. Such is the pace at which astronomy seems to be roaring ahead. And with that, I'll leave you with this fantastic picture of the Andromeda Galaxy showing all of those features. The nucleus in the center, imagine the narrowband image showing that that is itself a spiral, the ring structures around the galaxy that aren't spiral arms, all those dust lanes, all those star-forming regions, and the M32 galaxy, the dwarf that has punched through the center there and lost its outer layers. It's an incredible story, and so far advanced compared to when I first heard about the Andromeda Galaxy some 50 years ago. Well, thanks very much for listening, and I hope you've enjoyed that one.